So power series representations of function has played an important role in the development of calculus. As always, when we have a function, we're interested in certain characteristics or properties, such as continuity and differentiability. So I have a theorem here. It's called the properties of functions defined by power series. And if I have a function, f of x, looks like this. Sum from n to 0, n to infinity, 0 to infinity of a sub n x minus c to the n. That's our power series. We know what that looks like. A naught times x minus c to the 0 plus a first, x minus c plus a 2, x minus c squared, and on and on. So if it has a radius of convergence, which we've defined, greater than 0, then on the interval that we talked about, remember the interval of convergence, c minus r to c plus r, f is differentiable, so which also that means it's continuous, because if you're differentiable then you're already continuous, and the derivative and antiderivative integral of f are, well, f prime of x equals the sum n equals 0 to infinity. Think about what we do. It's n times x to the n minus 1. Okay. And the integral of f, remember it's the power series, n equals 0 to infinity of a n x minus c to the n plus 1 over n plus 1. And the radius of convergence of the series, if you integrate or differentiate, is the same as the original. So is as for the f of x itself. So for the derivative and integral is the same as the one, but the interval may differ. So we have to look at the endpoints. Still have to check the endpoints because with those two functions, it may be something different.